we've looked at some of the exams, and I think the mean will be higher than for the first midterm. So I've seen better scores this time than last time, including a few perfect scores. So it's looking good. And I'm guessing we should have all of the exams finished and the results posted for sure by Wednesday, but maybe even by tomorrow. Okay, but we have to continue. And I'm just going to take it right where we left it last time. And that's the last figure I showed you on whenever the last lecture was before the exam. And if you recall what we were doing, we had already studied the basic velocity potentials, the uniform flow, the source and the sink, the vortex, and we were just ready to start talking about the doublet, which in fact really belongs in this next section because the doublet is already a combination of basic potential flows, except for the fact that the combination results in a single potential flow, so that's why it is sometimes treated as a separate basic potential flow. But you might recall we were doing was we had studied the source and the sink, and what we did here is we took a source and a sink and put them on the x-axis a distance 2a apart. So the origin is right here, this blue coordinate system, and then letter A units to the right, that's where I have the sink, and then at x equals minus a, or a units to the left, that's where I have the source. And we discussed the fact that we would expect the streamlines to look more or less like I have sketched them here with a dash line. So we would expect that if you track a fluid element that leaves the source at some angle here, that then would eventually be captured by the sink. This source and this sink, by the way, have equal strength. So they are equally strong, but one is a source and one is a sink. And so we left it right at the point where I said, what do you think would happen if I now take this source and this sink and start bringing them together by moving each one of them closer to the origin? So I start moving the source to the right, and I start moving the sink to the left at the same, keeping them at the same distance from the origin, but closer and closer. In other words, we're taking the quantity A, we're taking A to go to 0. So we're saying, what would happen if I let A go to 0? And what do you think would happen? Suppose that I bring them exactly together so they're both at the origin. They would just cancel each other. They would just cancel each other and they would be left with nothing. However, if you remember the strength of the source, let me bring that figure back. When we looked at the source, we wrote the velocity potential for the source is some constant m over 2 pi natural log of r, and that constant, after we did a mass balance calculation, but looking at how much mass is crossing a certain ring of radius lowercase r, we found that really this m that appears in the source is really the volume flow rate per unit depth. And I told you it was unfortunate that it's called m because you think of mass flow rate, but this m happens to be the volume flow rate. So these two this source and this sink have the same m, but of course the sink is negative m. So it is true, if I bring them together, they would cancel out unless I do something else. What do you think I should do so they don't cancel out as I bring them closer together and they meet at the origin?
Increase the volume flow rate.
Yeah, if they have different m's, one positive, one negative, then they wouldn't cancel each other. So indeed it is increasing the volume flow rate, but not just one of them, but both. So I make the source stronger and stronger, but I also make the sink stronger and stronger as they come together. That way they don't cancel out. So what we want is, as we take A to 0, we want to take m to infinity, so that the product A times m, which would be undetermined because you have 0 times infinity, but I want that product to remain finite. So that's the condition that you impose as you bring them together. Bring them together, but at the same time make them stronger, so that the product of A times m remains finite. And if you do that, then you end up with what we know as a doublet. And indeed, it looks like a source and a sink that have been brought together, but they don't cancel out. So here's the same scenario, but a little bit more nomenclature illustrated there. So there is my source, there is my sink. The distance A is also illustrated there, but I also have now included the angles, because remember, the source and the sink are given in terms of those angles. Let me put this one back here for a sec, which gave us the, here in the red box, is the stream function for a source, whose m over 2 pi times theta. And theta was the angle measured when the source was at the origin. So it was coinciding with the theta of cylindrical coordinates. But of course now that's not the case, because now the source has been moved to the left at distance A. So the theta that appears here in this new configuration is theta 2. Right? And likewise for the sink, which would have this same stream function, except that it would be negative, the theta again is now the theta 1, because I have moved them. So they are no longer the theta from the cylindrical coordinate system. The theta from the cylindrical coordinate system is also shown here, is measured with respect to the x-axis, but from the origin. So now I have 3 angles to contend with: theta from the coordinate system, and then theta 1 and theta 2, which are the ones that I use in the expressions for the source and the sink, or the sink and the source in the same order. So if we do that, if we continue with that by bringing them together, so here is my source and here's my sink. Those are the same expression that I just showed you. The source, m over 2 pi theta 2 now, and the sink minus m over 2 pi theta 1. So I bring them together in a way that m times A remains finite, as I indicated in the previous figure. And so if you do that and you go through the mathematics of simplifying what happens, essentially you would be adding these two sides together. You would be doing, well, the full stream function for the combination is psi 1 plus psi 2. So you would write, well, that's m over 2 pi times a factor theta 2 minus theta 1. That's very simple. But if you continue working, it's essentially trigonometry, then you find that when you clean it up, then you end up with this. You end up with the stream function for the doublet is minus k times sine theta divided by r. And let me just check one thing very quickly here. That k is very likely, and I don't have it written here, but it should be the product that we kept constant. Let me just check. Oh, it's MA over pi. So let me write that here. So this K that you see here is MA over pi. All right. So it's the MA that we were talking about earlier that remains constant in the process of approaching them to each other, but it's divided by pi. So that's the stream function for a doublet. And if you go through the process of finding the velocity potential, the same way we've done it before, then you find that the velocity potential for the doublet is equal to that. So the stream function is minus k sine theta over r, and the velocity potential is k cosine theta over r. But so those are the mathematical results. But more interesting is to perhaps to take a look at what the field, the flow field, would look like. And remember, we're just bringing these two together. And what you end up with is something that looks like this for the doublet. And that's why it is taken to be a single basic potential. The doublet is, of course, at the origin, because that's where the source and sink ended up together. And as you can see, essentially it has the features that we saw here. Can you see both there? Maybe not, unless I shrink this a little. So, except that now it appears that the source and the sink are both at the origin. With the source, remember the source came from the left side and the sink came from the right side. So it is not surprising that towards the left side the flow is going out. That's why you see these streamlines on the left side, they're all going outwards. Of course they are going around just like they were here. And they end up at the sink, which is also at the origin, but it came from the right side, so not surprising again, we see that the streamlines are coming in through the right side. So that is what the stream lines look like for a doublet. Right? And you saw the equations a moment ago. So you want, okay, you know, does this have a meaning? It actually has a very significant meaning, because if I now take what I have here, if I manage to get it out, and I put it right here, like so, all right? What the doublet represents is the streamlines if you have a cylinder, which you can see right there in the center, moving from right to left. So if I have a cylinder, and it's a transient flow, it's an unsteady flow. So this cylinder is moving, is traversing the plane from right to left with a certain constant velocity. And this is what it would look like if I take a photograph, an instant photograph, when it is right at the origin. That's what I would see. But remember, this is an unsteady flow. So that's why you see if this is my cylinder, essentially what it is doing is pushing the fluid ahead of it forward. So as it moves to the left, it's pushing all this fluid out. That's why the streamlines go out like that. But of course, by conservation of mass, it suctions in fluid from the back. So as it moves from right to left, again, there is fluid coming from the back that is catching up with the cylinder. So that's the physical interpretation of what the doublet is. It's just the transient, the unsteady motion of a cylinder. In this case, from right to left, because I put the source on the left. If I had started with the opposite view, with the source on the right and the sink on the left, this would look exactly the same, but it would be going the other way. The cylinder would now be moving from left to right. Right? So that's an important application of what the doublet is. So it's the flow produced by a moving cylinder, right? Unsteady flow produced by a moving cylinder. All right. Any questions? Okay. So now we really start looking at superposition, even though, as I said, this came out of a superposition. We took a source and a sink and put them together on the same plane and brought them together to create the doublet. But if I now that we have this basic flow, so let's recap. We started the uniform flow, source and sink, vortex, and now we add the doublet to our list. What we want to do next is see what happens if I start superimposing those basic flows. And why is it that I can superimpose them? There is a very important reason why, even though we didn't discuss it here when we did this, why is it that I can take a source and a sink and take their expressions for velocity, potential, and stream function and just add them together? Why is it that I can do that? Does anybody know the answer? Why can I take a source and a sink and their individual stream functions or velocity potentials and add them up? That requires something.
The Laplace equation is a linear partial differential equation.
Yes, who was that? I know who you are. Okay, very good. That's the answer. Remember, both the velocity potential and the stream function for these flows that we're looking at satisfy Laplace's equation. We proved that earlier. The velocity potential phi satisfies Laplace's equation. The stream function psi satisfies Laplace's equation. And Laplace's equation is a linear equation. And because it is a linear equation, solutions can be added together to create new solutions. And that's the principle that we're using. Linear equations, so we can superpose solutions. You have two solutions, you add them together, you get another solution. You get another solution, added to those, you get another solution, which is valid. So we start now combining these. And the first one that is interesting to combine is if we take a source and add it to a uniform flow. What would happen? And so here's the picture of what we're trying to superimpose to each other. I have placed the source at the center, like we did when we first looked at the source. So I have a source, a line source at the origin. And now I take a uniform flow that comes from left to right, and I superimpose them. And I try to see what's going on. So what will happen if I start doing this? Tell me something that might be relatively obvious that will happen if I do this. Something that might jump at you by just looking at that figure. Alex, anything jumping at you? Well, I'm going to add them up. But can you see something that could be peculiar that will happen? Nobody?
The X components cancel out.
Where? Everywhere?
No, just at the origin.
No, the X components will not cancel out at the origin. Let me ask you a question. What's the velocity at the origin due to this source only to the source? It is infinity. Right? Remember, there was a singularity at the center. It is infinity at the center. And then it decreases as the flow goes out. Right? Because it's proportional to the inverse of R as it goes out. So it doesn't cancel here at the center, but can it cancel somewhere else? On the x-axis, which side of it? No? The negative side of the x-axis, because I see here, this velocity is always u sub 0, or u naught, to the right. This velocity, as I move from the origin out, decreases from infinity to essentially zero if you go to infinity, if you go far away. So obviously at some point this velocity will have the value of u naught at some point on the negative x-axis. Everybody see that? And therefore at that point, the two velocities being the same, and I am superimposing them, they cancel. And what do we have there then? At that point? We have a stagnation point because we have a point in the flow field where the velocity is zero. This is what the addition of the stream functions look like. Remember, we're superimposing, so we get the total stream function is the stream function for a uniform flow plus the stream function for a source. And here I have them from before. The stream function for a uniform flow was u naught times y, and the stream function for a source, we just saw it a while ago when we were building the doublet, is m over 2 pi times theta. So those are the two that I'm adding. But to add them, it is more convenient to have them in the same coordinate system. So the uniform flow is in a Cartesian coordinate system, whereas the source is in a cylindrical coordinate system. So what I'm going to do is I'm going to convert the uniform flow to cylindrical coordinates. And that's easy because I know that y is r sine theta. So here I have the same two added up together, but now they are in the same coordinate system. And if I now compute the velocities in cylindrical coordinates, u sub r and u sub theta, I'm only interested right now in u sub r. So u sub r from the cylindrical coordinate expression for the stream function is 1 over r partial psi partial theta. And I can obtain that because I just got that expression. So it's u naught, I'm dividing by r, so the r drops out of here. The derivative of sine is the cosine. And the derivative of theta with respect to theta is 1. So, and I am dividing by r, so m over 2 pi r. So here, on the last line, on the bottom line, I have the radial velocity in the combined flow field. Why am I looking only at the radial one? Because along the x-axis, that's the component that I'm looking for, the radial velocity that comes out of the source, right? So how do I define the x-axis in cylindrical coordinates? Actually, the negative x-axis. What is this axis from 0 to the left in cylindrical coordinates? Theta equals pi. That is correct. Theta equals pi. Whereas theta equals 0 would give me the positive x-axis. So what I do want to look for is this radial velocity along the negative x-axis. And so I need to put theta equals pi, which makes the cosine of theta equal to what? What is the cosine of pi? Huh? No. Negative 1. Negative 1, right? You should know this because you were supposedly doing calculations of v dot n, right? And when they are opposite, it was minus, right? So I am setting this to 0 because I'm looking for the stagnation point, so I need to have 0 radial velocity. And then I'm going to put theta equals pi. And if I put theta equals pi into my expression here for the radial velocity equal to 0, then of course cosine of pi is minus 1, so that becomes minus u naught. The radial velocity due to the source doesn't depend on pi, right? It's the same everywhere, so that stays as m over 2 pi r. And I'm setting that equal to 0, and then if I solve, I get the location, the radial location of that stagnation point. It's located at m over 2 pi u naught. So that's, maybe we can start building a plot here separately. So here is the coordinate system. The source was here at the center. Let's not use that one, it's too thin. The source is here at the center. And again, I am looking for a place somewhere along this axis where the velocity is 0, so that's a stagnation point. And I just found that the distance to that stagnation point is m over 2 pi u naught. So that's, if you want to sketch it here, that's this distance. This distance is m over 2 pi u naught. Right? I just found that location right there. And I know that the streamlines to the right of that stagnation point come this way because they come out of the source, and the streamlines on the, the streamlines on the left side go that way because they come from the uniform flow, and that's where they cancel at that stagnation point. Okay, so what is the theta velocity at the stagnation point? The theta velocity in the direction of theta. We just found the use of r, set it up to 0, but what about use of theta? What is use of theta there? Nobody knows? 0. It is 0, right? It is 0. Because there is no velocity normal to the x-axis by symmetry. If I just look at what I'm building here, from symmetry, we see that there cannot be a theta velocity right there, anywhere on the axis. All we have is a velocity in the radial direction, or in the x direction for that axis. So there is no use of theta. That's why I only looked at use of r. I didn't look at use of theta. All right, so now that we have found that there is a stagnation point there, what do you think happens to the streamlines? There's two streamlines that are coming in and are meeting at that point where the velocity is 0. What happens to the fluid that is going that way? There is no sink there. There is no sink there. That's just a stagnation point. So the fluid that is coming from the right is arriving there with 0 velocity, and the fluid that is coming from the left is arriving there with 0 velocity because that's where the stagnation point is. But what happens to the fluid? There is fluid going that way. Huh?
Does it become like a source?
No. Can you see that it has to go off somewhere in another direction? So it has to go out, we guess, that way and an equivalent way down, but I'm just going to clutter my diagram because I put SP there. But it's going to go down this way, somewhere. Yeah? It has to go somewhere. It's coming, meeting there, has to go out somewhere. How do I find that? Well, the way we find it is, let's first of all find the value of the stream function at that point. What is the value of the stream function at that point? Here is the stream function. We found that a little while ago, right here. Psi is u naught r sine theta plus m 2 pi theta. Let's evaluate that stream function at that point. What are the coordinates of that point? Well, they are r is equal to m over 2 pi u naught. So that's why I'm plugging it right there. All right. And theta, we said, is pi. So if I just plug that for r that I just found, and plug theta equals pi in that equation for the stream function, I can evaluate the stream function at that point, just like we did in the simpler problems earlier, where I said, find the value of the stagnation, of the stream function at a certain point. You would just plug in the coordinate systems in the stream function and get the value. That's essentially what we're doing. We're plugging in that. And we find, of course, that the value of this stream function at the stagnation point is m over 2. Because the sine of pi is 0. So the first term doesn't contribute anything. And the second term just contributes m pi over 2 pi. So m over 2. So I just found that the stream function, this stream function that meets here, has a value of m over 2. And of course, what is the value of the stream function on this line and on this line? What is the value of the stream function on the line that is approaching the stagnation point? I know the value of the stream function at the stagnation point. What is the value of the stream function on the approaching lines, on the approaching streamlines?
0.
Nope. It has to be that same value. Right? It has to be m over 2, otherwise they wouldn't be streamlines. Right? A streamline is characterized by a unique value of psi. So m over 2 is correct. So the stream function is m over 2 all the way from the origin to that point and all the way from minus infinity to that point, because it's the same streamline. So if I now take my expression for that I just found for the value of the stream function at that point, which is m over 2, but I set it equal to the entire stream function. So all I'm saying is I'm taking this expression that I found earlier for the stream function and I am setting it equal to m over 2. So there it is. U naught r sine theta plus m over 2 pi theta is all right there. But I'm setting that equals to m over 2. And let's see what happens if we do that. Set that equals to m over 2. Solve for r. Solve for r. Then we get r equals m over 2 pi u naught times pi minus theta over sine theta. Okay. All right. So again, what was the, remember, that's the m over 2 is the value of the stream function at the stagnation point and also on the approaching line. But if there is a streamline that is indeed coming off from there, it has to have the same value of psi, m over 2, because it's also a streamline. So what this equation is doing for me then is telling me the shape of that streamline that I was looking for. This equation that I put in the box, r equals m over 2 pi u naught times pi minus theta over sine theta, is the equation of this streamline that I am very interested in at this point, that comes off the stagnation point. So what I have is there are two streamlines that come in and meet at one place, the stagnation point. They have the same value of the stream function, and then that streamline branches out up and down, right, for conservation of mass, into another streamline that has a different shape, but it has to have the same value of the stream function. So, and it is right here. What does this equation look like? Suppose I ask you to plot this line. Right? We know it starts from here, right? And it goes off. Which way does it go? Which way do you think it goes? I kind of hinted at it by the way I drew it. The way I drew it, I gave a hint that it's kind of going to the right. Right? That is not too surprising, because if you look at this, right, and you try to find the velocity somewhere here, and it's the addition of the uniform flow plus that, and if you do the vectors and you do it right, you find that indeed there'll be it'll be tilted to the right. It'll be up and tilted to the right. It's a lot easier to see what it looks like on a point like here in the back, because I have the source going that way and the uniform flow going to the right, so that's clear that it will give me some vector that way. But what does the whole line look like if I plot this? Well, what does it look like on the y-axis? What is theta on the y-axis? What is the value of theta on the y-axis?
Pi over 2.
Theta equals pi over 2. All right? So let's plug that in there and see what happens. We get r equals m over 2 pi u naught, and then times Pi minus pi over 2 is just pi over 2. And sine of pi over 2 is 1. So I get R equals M over 4 U naught. That's the place where this line will intersect the y-axis, because that's this distance. This distance that I calculated here is that distance. Move that up a little. All right. So I know that the streamline intersects the y-axis at m over 4 u naught. All right. And remember, the intersection on the x-axis, which is my original stagnation point, was at m over 2 pi u naught. Which distance is larger? The one to the stagnation point, from the stagnation point to the origin, or from this intersection point to the origin? Which of those two is larger? Yeah, because 2 pi is over, well, take that back. 2 pi is larger than 6, right? 2 pi is larger than 6. This is 4. So this distance is shorter, right? Because you're dividing by 6 versus dividing by 4. So it's kind of the way I sketch it here. It looks like this is a little farther, right, than this. What about on the bottom side, on the negative y-axis? Where does it intersect? On the negative y-axis. Where does it intersect the y-axis? Yeah, symmetry, right? So the same point down there. All right, so we got 3 intersection points for that streamline. It intersects here, it intersects there, and it intersects there. Could it intersect the x-axis somewhere else?
No.
Farther down there, why not?
Because your streamline on the x-axis is going in the same direction as the uniform flow.
Very good. So if I just look at this original diagram, if I look at any point on the positive x-axis, there is no way that there'll be a stagnation point there. Because, like he said, both velocities go to the right, due to the source and due to the uniform flow. So they cannot cancel each other on the right-hand side. So where does this line go then from here? Where do you think it goes? It takes a little bit of thinking. Actually, let's do it right here. Here's the expression for R, right? So let's put it in terms of y. Okay, so let's take this very same expression, but instead of writing R, right, remember R is y over sine theta, right? Because y is r sine theta, right? So I'm going to leave the rest the same. M 2 pi u naught pi minus theta over sine theta. The reason why we do this is because if we write it in terms of y, then it's convenient because we can get rid of this sine theta that appears on both sides. Right? Cross that out, cross that out. Okay? So let me write this expression in clean form. Y equals m over 2 pi u naught, and then just pi minus theta. Right? Why am I writing that expression like this? Because I want to find out what happens to this line as I go very far. Where is very far in terms of theta? What theta? Theta equals 0. So to go very far, you go to theta equals 0. And of course, that's why it was convenient or necessary to make this adjustment, because otherwise I would be dividing by a sine of 0. So, but I can put here theta equals 0. Right? So if I put theta equals 0, then I get y equals m over 2 pi u naught I'm putting theta equals 0, so I just get a pi, cancels with the pi, m over 2 y naught. What is this telling me? That I find that the value of y on the line is equal to that as theta goes to 0. Anybody see what happens? Since you picked theta equals 0 for far away, what is that telling me? A horizontal line. Very good. So where we're getting is that as you go far away, this will approach some horizontal line, okay, which is this much far from the x-axis. So let me show you a clean picture of what that looks like. What we just did was this. Find this shape. Actually, I have a much nicer one here. Right. So this black streamline, I chose it to be black, is the one that I'm going to put these two side by side there so you can see them both. Right. Because in the figure on top, I am also showing the streamlines inside that streamline. So what I have found is that there is a streamline here that I drew in black in this upper figure that is the one that takes the shape that we were just looking at. As I go far away, it is m over 2 u naught away from the x-axis. So in the top figure, you have the whole flow field. Outside that streamline and inside that streamline. You can see how essentially what is happening is that the uniform flow is like blowing on the source, right? And making the source streamlines bend like we see in this figure. But the magical thing about this about this streamline that we just found, and that's what I did the second plot, where I drew that streamline in a solid curve, is that I can use that to be actually an object. The so-called dividing streamline, which is what we just found, the dividing streamline that came off of the stagnation point is still right here, can be used as the surface of an object that is put in that flow field. And I don't really care what the inside looks like because I don't need that part. That's why I drew this other drawing where I just put dashed lines inside, because this is like if I have an object that has like a blunt nose and is in this uniform flow field. Now the source for me is not relevant. It does produce this pattern, but I can just see this as now, this is the flow field around this body. And we call that, what happens to the back end of this body? To the right. It doesn't end. It keeps going. Because again, if you look at the top figure, that line just keeps going. So that's why we call this object a half body. This is a half body. Because it's like the front half of an object. It doesn't have a back end to it. Right? So, all right. We just figured out everything about the width and so on. So, the next thing that we want to do, let me see any questions about how I came up with the half body. Okay, so the next thing that you want to do is, could I possibly find out what the pressure field is in this flow? Let's find out what the pressure field is in this flow. Might be interested, for example, if you want to find forces on this object due to the fluid. Right? Now, what's the velocity on the surface of this half body? What's the velocity on the surface of this half body? In reality, that would be correct. But in this one, is it 0? The hint to the answer is actually right here, right? There is the stagnation point. right? I'm still drawing arrows on that streamline because that's a streamline, right? Remember, that was the flow that met at the stagnation point and then went off to the sides, up and down. So in reality, if I have an object like that, of course it would be 0 because I would have no slip condition. But can I impose a no slip condition on this flow? What type of flow is this that we're just looking at? Describe this flow. Give it adjectives that belong to this flow. Steady. What else? Incompressible. What else? Before we say non-viscous. But somehow related to that. What do I need to create a velocity potential? What does the flow have to be for a velocity potential to exist? Irrotational. Irrotational. We're dealing with stream functions and velocity potentials all the time, even though we're just looking at the stream function here, but we can write a velocity potential. This flow is irrotational, right? So in the real world, if I put an object like that in a fluid that has viscosity, what would happen at the wall, near the wall? What would be created near that wall? Rotation, vorticity, right? So this flow is irrotational. So the only way to retain the condition that the flow be irrotational if we assume that it's inviscid. Right? That's why when we look at potential flows, most of the time we make the connection, well, it's irrotational, and if I have a wall, then it has to be inviscid, otherwise there would be rotation. So this is an irrotational flow. We can think of it as an inviscid flow, and therefore there is a velocity on the surface of the object. It's not 0. There is a velocity there. You have to understand that that's obviously a limitation of the theory, but that doesn't make it useless. So I can find what that velocity is because I have the expression for the radial velocity from before. We used it to find the stagnation point. And I can now start dealing with the other component, with the theta velocity, which I can also find by taking negative partial psi partial r. So actually I have the expressions for the velocity components anywhere, for any value of r and any value of theta. How do I find the velocity on the surface itself? I would have to put the condition that r is whatever it is on the surface and theta is whatever it is on the surface. But let's not do that yet. Let's just find the total velocity, the square of it, by taking the components and squaring them. So I'm going to take u sub r, I'm going to square that. I'm going to take u sub theta and square that and put them together, and I get that expression there. After cleaning up the numbers, the symbols, right, during squaring it. So to simplify our notation, because this factor appears all the time, m over 2 pi u naught appears all the time. So I'm going to just call that b. M over 2 pi u naught. Remember, that was the distance from the source to the stagnation point. That was this distance here in the front. From here, from the source to the stagnation point, that was m over 2 pi u naught. I'm going to call that b. So if I do that, if I call that b, then my expression for the velocity, after substituting that, is only to clean things up, becomes that. All right? U naught square factor of 1 plus 2 b over r cosine theta plus b squared over r squared. This expression gives me the velocity field, the square of the velocity, the square of the speed actually, because there is no vector anymore. I have squared the components and added them up like that. Now, can I use Bernoulli's equation for my flow? Can I use our Bernoulli equation from chapter 3? Yes or no? Yes, we can. All the conditions are met. So if I do that, then that's my Bernoulli equation. P naught is the stagnation. Is the pressure far away. So if I do that, P naught is far ahead. Then I can plug this velocity square in here, and I have an equation that I can use to find the pressure. So I'm kind of summarizing it because, you know, you would now take this v square and plug it in here and then solve for p. But all I want you to know is that you can do that. There is a tool. You can find the pressure field if you just take the Bernoulli equation, because we satisfy all the necessary conditions, and we can get the pressure that way. Let me ask you one thing before we go. How could I close this object? So let me get my drawing again right here. How could I close the back of this object? You put a sink somewhere back there on the right. If you put a sink somewhere back there, then the object is no longer a half body. It has an end. It closes on the right side. We'll talk a little bit more about that next time.